Good morning, everybody, and thank you for listening. This is our presentation of control and optimization of a zero carbon power grid. This is our final project for dynamic optimization. I'm Cameron Price.
Tyrell Hess.
And Derek Prestwich.
So the premise of this project is that we wanted to create a power grid that could satisfy variable demand while optimizing a combination of energy sources. At the same time, we wanted this energy supply system to minimize over and under production. We wanted to accomplish this and did accomplish it with using nuclear, solar, wind, and hydropower, a completely carbon-free array of energy sources. However, to do this, we did assume that nuclear load following would be profitable. That's currently not the state of affairs in the nuclear industry, but just assuming that that could become profitable, we created this kind of proof of concept energy system.
So to implement our research, we created a digital twin. And here's our model that represents that digital twin. It consists of a primary loop that circulates the moderator through our nuclear reactor, which then takes the heat from there and it exchanges it with a coolant loop, which then brings that energy over to the turbine and thereby provides our load. We modeled this nuclear reactor using the point reactor kinetic equations along with 6 delayed neutron precursor groups. We also have our heat transfer equations, and then at the bottom we also have an expression for the reactivity of the neutrons within our nuclear reactor. It takes into account the effects of temperature and also the nuclear control rod position U, which is our actuator. So here's an example of our model, simulation being run for a step test. As you can see, every single time there is an increase in power, there is this slight spike that occurs, which is exactly what we would expect in real life, and also it is exactly what we have seen in the literature. This is caused by the sudden reaction of reactivity in response to the sudden increase in temperature. So as you can see that as temperature increases here as well, there is a slight decrease in reactivity in response, and that also brings to this a slight decrease in the power as time continues on. So here we have our reactor step test results with our model predictive controller, and as you can see, apart from this initial overshoot, the controller works very well and stays very consistently with the set points. Also of interest down here is our moving horizon estimator, where it continuously updates the value of U, which is our overall heat transfer coefficient. We selected this parameter to estimate because of its potential to change because of fouling and also changes in thermophysical properties because of temperature changes. Also, in this graph over here, we have temperature profiles and also the changing positions of the control rod over our 5-day simulation. And of particular interest is this blue line right here, which is our coolant temperature. And we're very happy with this result because one of the constraints of our system is to maintain the temperature of water below 375 degrees Celsius, which is its critical temperature. And our system has been able to successfully do that.
Here's a plot of our 5-day simulation in which we integrated several energy resources with the controller that Tyrell just described. As you can see, we've got some solar energy that occurs periodically, which is in yellow, and some wind energy that is fairly variable here in green. And this energy combined with the nuclear power in red needed to fulfill this entire demand profile here in black. So because solar and wind were not controllable, they simply removed a portion of that demand at any given time and created this line in gray, which is the demand from nuclear, which is also at times satisfied by some of the hydropower. Now, the most unique portion of this integrated system is the combination of the hydropower with the nuclear power. What we've done is we've implemented a PID controller that regulates the level of the reservoir at any given time. And that PID controller also feeds this parameter to the objective function of our model predictive controller, which allows us to kind of have this separation that you see right here at about time 25 to 40, where the demand is being fulfilled not by the nuclear power supply anymore, but by the draining of the reservoir. That's useful because there might be times where you're expecting a rainy day, and so you can drain your reservoir, and then later on that reservoir can be refilled by the rain, as is simulated here at about time step 80.
So what we accomplished in this project was create a simulation that shows that using this combination of energy sources, you can meet variable energy demand. In particular, as we've discussed, we were using nuclear, solar, wind, and hydropower. So it's a proof of concept for carbon-free energy schemes, things that could be used particularly if nuclear load following was a profitable venture. And that's something that should be explored. There was no economic analysis performed in this project. We simply looked at the technical feasibility, and so an economic study, of course, would need to be part of any future study or research into an energy system like this. Additionally, the point kinetics model that we used, we made several assumptions that simplified the computations and calculations, but ultimately, moving forward, it would be best to look into those models and add more detail to those point kinetics models to make sure that they are as accurate as they can be to describe the nuclear reactor and its dynamics. Thank you.